I'm Dr. Paul Houle, and the purpose of this program is to help prepare the viewer to take and pass the EPA's new RMP exam. Now, the RMP exam is focused on 7 different topics, and so this video program is divided into 7 different parts. The first part, which we will begin in just a moment, will be on very fundamental nuclear physics to get us started. In the text that you have with you, you have copies of the visuals that you'll be seeing on the screen. And I would recommend that you have that appropriate visual in front of you as you see them on the screen so that you can make notes for yourself right on the visual in your text. And that will help reinforce what you'll be hearing and learning as we progress through the program. Also, periodically, we'll be stopping for you to exercise some questions which are properly located within the text. And the answers to those questions are at the end of the text. However, I suggest that when we get to those points where I tell you to do the questions, that you answer all the questions to the best that you can. And when you're done answering all those questions on that part, then to go in the back of the book where the answers and explanations are and look up the answers and explanations and satisfy yourself that you understand the material. And we will move our way through the program in all 7 topics in exactly this way. I'll have a little bit more to say about the questions when we come up to our first set of questions. So let's begin. The very first topic is very fundamental nuclear physics. And I underline the word very here. Nuclear physics is not nearly as difficult as you might think it is. Beginning, it's very simple. We have matter is made from the elements, and elements are made from atoms. The little red dot that you see on the screen is just my pointer. The atoms are generally taken to be the fundamental building blocks from which we create all the matter that does exist. And any one atom is built up, as you see here, in this next visual. The atom covers a certain area, and in the center of that area, called the nucleus, are the protons and the neutrons. And then surrounding the outside of that are the electrons. Now, the protons are positive, and that's fairly easy to remember. Protons are positive. Electrons, they have a negative charge, and so I've drawn them with an E with a little minus sign next to them to indicate that they are negatively charged. And the neutrons have no charge. They're neutral, so that's easy to remember too. Neutrons are neutral. Now, the entire atom, typically, the most common way you find an atom is where the number of electrons and the number of protons is precisely the same. So the positive charges that are on the protons cancel with the negative charges that are on the electrons. So the total charge of an atom typically is neutral. Usually you find an atom in a neutral state. Now, some of the terminology with which I'd like you to be familiar is on this visual. The atomic number is simply the number of protons in the nucleus, and the atomic weight is the number of protons plus neutrons in the nucleus. And to exemplify this, you see on the next visual that hydrogen is given the symbol H for the element hydrogen, and then the picture of it that you can have in your mind is that the nucleus consists of one single proton, and the one on the bottom of the H represents that proton. The number of protons in the nucleus is indicated by the number on the bottom of the element symbol. So the atomic number for hydrogen is simply 1, the number of protons. The atomic weight for hydrogen, since there's only one proton in the nucleus, there are no neutrons in the nucleus of hydrogen, the atomic weight is the number of protons plus neutrons, which is also 1. And so hydrogen is typically written as 1H1, as you see here. And I've also indicated that there's 1 electron, so that the total charge of the hydrogen atom is typically 0. The helium atom, similarly, has 2 protons and 2 neutrons in the nucleus, and it has 2 electrons surrounding it. Again, the net charge on the helium atom is typically 0. The 2 represents the number of protons in the nucleus, and therefore that's the atomic number. The 4 represents the total number of protons and neutrons. There are 4 of them in the nucleus, and so that's the atomic weight, taken as 4. Radon, our favorite atom, has 86 protons and a total of 222 protons plus neutrons in the nucleus. And so somewhere around the nucleus are 86 electrons, typically, so that, again, the radon atom is a neutral atom. Now, at this point, this is where we come to our first set of questions. And what I would like you to do is on the very next page of the text is a page of questions, and I would like you to answer all of those questions. And then go to the end of the book, look at the answers, and see if you agree that your answers agree with my answers, and they should. Then return to the video at this point. I hope you had some success with dealing with those questions. Moving along, the units of energy is the next topic that I want to discuss. And you're already familiar with some units of energy, of course, the kilowatt hour. Your electric bill is based on the number of kilowatt hours you use in your house, and that's a form of energy. Number of gallons of gasoline, that's a form of energy. Barrels of oil, tons of coal, those are all forms of energy. Now, in the nuclear arena, however, those units would be way too big. And so we have another unit called the electron volt. And it's just like a kilowatt hour. It's not exactly the same number, but it's very similar to that. It is a form of energy, the electron volt. And to get you some idea of what that is, in this visual here you see that I've drawn in a 1-volt battery, and I've placed an electron here in between the 2 plates that would be created. There's a voltage difference in this drawing of 1 volt between the negative plate and the positive plate. And if I release an electron at this point, as you see here, the electron will be repelled by the negative plate and attracted by the positive plate. Now, you might remember that like charges repel and unlike charges attract. And that's why you see the electron is going to be repelled by the negative plate and attracted by the positive plate. So if I deposit the electron here at rest, it's going to accelerate to the left, and in so doing it's going to gain energy, the energy of motion. And the amount of energy that it's going to gain as it traverses this 1-volt difference we call an electron volt of energy. So that's the unit. It's a very small quantity of energy. Now, so we have multiples of the electron volt available to us as well. We have the electron volt, which you now have an understanding of. We also have units of thousands of electron volts, and 1,000 electron volts is usually written as 1 keV. K, the typical symbol for 1,000. So that would be 1,000 electron volts, and similarly, 1,000,000 electron volts is written as 1 MeV of energy. The types of radiation with which we will need to be familiar are, as you will see in this visual, betas, gammas, and alphas. And here, you'll note the beta particle, typically given the symbol, this squiggly B, is really just an electron. That's all it is. The alpha particle is simply 2 protons and 2 neutrons bound together. And so you might recognize this as the nucleus of the helium atom. The symbol for the alpha particle is the Greek letter alpha. And gamma rays, who have the symbol gamma, and I've drawn them as a picture as a little squiggly wave here, is just a form of electromagnetic radiation. Gamma radiation is just like visible light, except that its frequency is much higher. And whereas, for example, there's visible light striking my body right now, and I can feel the energy of that visible light, gamma radiation is just like that, except it's so high frequency that it's not noticeable by the human eye. And it tends to carry a lot more energy than visible light as well. To return to the beta particle for a moment, I just want to point out that this is an electron, just like we've seen in the earlier visuals. But the reason it's called a beta particle is because the origin of this electron, rather than having been generated at the outside of the atom, that is outside the nucleus, the beta particle is generated inside the nucleus and emitted upon its creation. And so we give it the name beta particle, even though it's exactly the same thing as a regular, everyday electron. to remind ourselves that that particular electron came from the nucleus. Now, to look at the kinds of energy, how much energy is carried by the different types of radiation, we see here that radio waves, for example, carry 1/1,000,000th of an electron volt. So radio waves carry extremely small amounts of energy. Visible light carries between 1 and 3 electron volts, ultraviolet between 3 and 10, X-rays between 10 and 120,000 electron volts. The amount of energy now is increasing a little bit. Gamma rays from a few thousand electron volts up to 10 million, betas from a few thousand to a million, and alphas from 4 to 8 million electron volts. And what I would like you to get out of this visual especially is that the alphas typically carry the most energy than any of the others. Now, I admit that the gamma rays can be up to 10 MeVs, although that's quite unusual. And typically the gamma rays will be down in the keV region. They'll carry a few thousand electron volts. The alphas, therefore, I want to claim, typically carry the most energy of any of these other kinds of radiation. That makes the alpha particles typically the most dangerous. Now, the alpha particle itself, as you saw, was a helium nucleus, 2 protons and 2 neutrons. And here I've delineated some of the properties of the alpha particle. The mass of the particle, it's very heavy. Now, that doesn't mean that it weighs a pound. Obviously, these things are nuclear particles, so they're extremely light in comparison to everyday phenomena. But in relationship to electrons and protons and neutrons and gamma rays, etc., the alpha particle, compared to those, is quite heavy. The charge of the alpha particle is +2. Remember, it has 2 protons in the nucleus. And the range of the particle, how far it goes when it's created, is very short. Note, I've indicated 3 to 4 inches when it's in air and 1/100th of an inch in tissue. Now, I want to talk about this for a moment in the sense that because the alpha particle is very heavy and carries a significant amount of electrostatic charge, +2, its range is very short. It's because it has a lot of charge and it's a fairly large atom, a fairly large particle, that its range is very short. That is, when it strikes a material, it can't get very far because it's so big, and because it has a lot of charge, it interacts very rapidly with the material that it strikes immediately. And so its range is very short. Now, the point I would like to extrapolate to here is that it's going to deposit that 4 to 8 MeVs of energy, which on the nuclear level is quite a bit of energy. It's going to deposit that energy in a very small range of tissue if it's striking a piece of tissue. And because it's going to drop all that energy in that across just a few cells, it can do a lot of damage to those very few cells. If we took that 4 to 8 MeVs and deposited it across 2 miles of tissue product, then it would deposit that 4 to 8 MeVs over a very large distance. And the amount of damage it would do at any one point would be very small. In effect, we spread the damage out. But the alpha particle doesn't do that. It deposits all of its energy in a very short range and does a lot of damage to just a couple of cells, or just a few cells. If those cells are regenerating themselves and they've been damaged, then they have the potential for regenerating themselves in damaged ways, which we then recognize to become cancerous tissue. Okay. The beta particle, on the other hand, to continue on, remember that's just an electron, and this guy is very light. The electron's very, very, very light. Charge -1, so it has half the charge of the alpha particle, and so it's not going to interact nearly as much, and because of that, you'll note the range is from 0 to 30 feet in air and a few millimeters in tissue paper. So the beta particle, it's not nearly as dangerous, first of all, as the alpha particle, because first of all, the beta particle carries a lot less energy. Secondly, because its range is much larger than the range of the alpha particle, it will deposit that energy over a larger region, doing less damage per inch, you might say. And so the beta particle is not as dangerous. I should also point out at this point that the beta particle can make it through one or two sheets of paper without much trouble. The alpha particle, if you held a sheet of paper in front of the alpha particle can't even make it through the sheet of paper because it interacts so highly with just the material that's in that piece of paper, just that little thickness that you see right here. Coming down to the gamma ray, or the gamma particle, which is also emitted by the nuclei, here, this is quite amazing. The gamma particle has no mass. There aren't too many things with which you're familiar, I think, that have absolutely no mass whatsoever, but the gamma ray has no mass. Remember, it's very similar to visible light. It has no charge. And because it has no mass and no charge, it doesn't interact very well with matter at all. And so its range is very long. Gamma rays pass, in most cases, right through your body without stopping or slowing down. And if they don't deposit, therefore, any energy into your body, they can't do any damage. Okay? So the gamma rays are not overwhelmingly dangerous. I'm not suggesting that if you immerse yourself into huge intensity of gamma rays that you won't be exposed to a significant health risk. You would be. But in the typical gamma radiation that we're immersed in every day, even as we speak here, the gamma radiation is not a particularly large health risk. Now, having said that, looking at the health risks, I've pointed out here on this visual that alphas and betas, I've grouped them together. Their health risk is low if it's external, that is external to the body, and the health risk is high if it's internal to the body. Gammas are low or high depending on intensity and duration, and really for all intensive purposes, unless you're in a very high concentration of gamma radiation, which we do not typically see in the radon arena, only the alphas and betas have a potential of doing some damage. And as I pointed out, the alphas, which deposit most of their energy in a very small range, are incredibly more dangerous than the betas. Now, I want to spend a moment talking about the fact that the health risks of the alphas and the betas are low if the radiation is outside of your body. And let's look at this. If the alpha particle strikes the outer surface of my skin, it deposits all its energy in the first few cells. Now, the outside of the human skin is actually a pretty tough material. And if so, an alpha particle strikes that tissue right there and damages some of it. Actually, when I do this with my hand, I wipe the damage right off. Because when you rub your hands, you're rubbing away a large number of the surface cells. So, excuse me, the damage is easily removed. Also, the outer surface of your skin has evolved to be a very tough surface. Whereas the inside surfaces of your body, such as the insides of your lungs, those tissue surfaces are not nearly as resilient as the outside surface of your skin. And so if an alpha particle does some damage, if it strikes a tissue on the inside of your lung, then that tissue will be damaged. There you can't wipe that away. And again, with no way to get rid of the damage, as that cell tends to regenerate itself, then the effect of the damage can be propagated into the other cells that are being regenerated from that original damaged cell. So the upshot to this is that the health risks of radiation are high if they're internal to your body, that is, if the radiation is internal, and it's very low if the radiation is external. Okay. The next topic is the topic of half-life. And as you see here, that is the time it takes for half of the atoms that you have at a given moment to decay. Now, these atoms, what we mean by radioactivity, is that if you're given a container of atoms, here I have a 1 liter bottle, and if I have a 1 liter bottle full of atoms, if I wait, let's say there's 1,000 atoms in here, radioactive atoms, what I mean is if I wait long enough, those radioactive atoms, they explode. We typically call it a decay. Each atom will, in turn, as the time goes by, decay. And so if I start with 1,000, say, radon atoms in here, and I wait a given amount of time, I'll have 900 atoms, and then 900 radon atoms, and then 800 radon atoms, and 700. And the total number of radon atoms that we have in the container as time goes by decreases. And the measure of that we call the half-life. Again, you can see that in one half-life then, if you start off with 200 atoms, that after one half-life you have 100 atoms. After another half-life you have 50, etc. Until eventually, after a long enough time, you have no atoms at all. Let's take a look at an easy example. Suppose you start off with 5,000 radon atoms, as you see here. Right now, at this moment, you have 5,000 atoms. How many are you going to have after 12 days? Bearing in mind that the half-life of radon is 4 days. Now, the half-life of every radioactive element is different from that of every other one. Not all atoms have the same half-life, obviously. And radon has a half-life of just 4 days. So, if you start off with 5,000 atoms, after 4 days, you'll have 2,500, half of what you had before. After 8 days, you don't go to 0, you go to half of what you had before, so you go to 1,250. After 12 days, you go down to 625, going down by half as much in every half-life. Take one more example of this type, and we'll do the problem backwards. If we want to be good at doing the problem frontwards, we should also be good at doing the problem backwards. Let's consider you have 250 polonium atoms. Now, the 218 is just the atomic weight of this polonium. And so let's suppose you have 250 of those atoms right now. How many did you have 9 minutes ago? Well, the half-life of polonium-218 is approximately 3 minutes, a very short half-life. And so if you have 250 now, one half-life ago, you must have had 500. 6 minutes ago, which is 2 half-lives earlier, you must have had 1,000. And 9 minutes ago, you must have had 2,000. So we can see that going backwards, of course, we get an increase in the number of atoms, and always by a factor of 2 for every half-life that transpires. Again, at this point, I've placed a series of questions immediately following this visual, and I'd like you to deal with them as we have been doing, and then return to the video at this point. Again, I hope you had success with the questions you were working on. In any case, we're going to move along. The next thing I want to look at is, where does radon come from? Where do all of the radioactive elements come from? And they are all part of what are called radioactive decay chains. And if we can look at this very next visual, you will see that I've depicted here the uranium-238 decay chain. And the uranium-238 is a radioactive element, and at the beginning of the universe, that is, if you believe in a Big Bang theory, at the very initial creation of our current state of the universe, there was some uranium-238 generated. And that was radioactive, and it decays by the emission of an alpha particle, as you see depicted here, with a half-life of 4.5 billion years, which is, of course, why we still have some uranium-238 left. The current estimate of the lifetime of the current universe is about 4 billion years. That is, the Earth has existed for about 4 billion years, give or take a few minutes. And so that's why we still have some uranium-238 left. Half of it is gone. It has decayed down. But in any case, the U-238 decays down by the emission of an alpha particle, and when it decays, it doesn't simply disappear and become nothing at all. It leaves another atom behind. And in this particular case, it's thorium-234. Again, remember, these are simply the atomic weights. And the thorium decays. It has a half-life, it too is radioactive, of 24 days. And it decays to uranium-234, which then decays by the emission of an alpha particle to thorium-230, half-life here approximately 100,000 years. The thorium-230, we continue this game, decays by the emission of another alpha particle in, again, about 100,000 years to radium-226, and now we're getting very close to radon. Radium-226 decays in approximately 1,620 years by the emission of an alpha particle into radon-222, and that's the atom that we're concerned about, is the radon-222. Now, in that picture that you just saw, of all those different atoms, the uranium-238 right down to the radon-222, the interesting thing is that all of those elements, all of those different atoms are solids, except for radon. Radon is the only one in that chain that is a gas, and that's why radon has become a problem. The uranium you can find anywhere beneath the surface of the earth, and you don't have to go significantly deep. You can reach down with your hand, grab some soil, and I assure you there'll be some uranium in there, perhaps not much, but there will be some. And as the uranium decays into its daughters, the nuclei that it leaves behind, its daughters, its progeny, as it decays down into those daughters stay in the soil because they're solids. It's not easy for them to escape. But when the radon finally comes into existence, when it becomes created, since it's a gas, it has the opportunity to be quite mobile within the soil and to percolate up through the soil. If you've built your house on top of a region where there's a significant amount of uranium-238 or a significant amount of radium-226, as that decays down into radon, that radon has the opportunity to percolate up and potentially enter into your house. Let's continue on now. That's not the end of the uranium decay chain. This chain goes on continuously, and it looks a little more complicated in this visual, but it isn't. If you'll bear with me for a second, this is really another simple continuation of the decay chain. Starting now at the radon-222, emits an alpha particle and has a half-life of 3.82 days. Earlier I was taking it as 4 days, and you'll see that it's pretty close to 4 days. When it decays down to polonium-218, which I have underlined for a purpose you will see in a second. Now the polonium-218 actually can decay in either of two ways, either by the emission of a beta particle, in which case it becomes this atom, or the emission of an alpha particle, in which case it becomes this atom, lead-214. In either case, whether it becomes the astatine atom or the lead-214, both of those will decay down into bismuth-214. And the bismuth has an opportunity to decay either by the emission of an alpha particle to tellurium or by the emission of a beta particle to polonium-214. And again, it doesn't matter because both of those will decay down to lead-210. And the decay chain continues on ad infinitum almost down to lead-206. And lead-206 is a stable atom. It is not radioactive. And that terminates the decay chain then. Now the reason I've underlined the three atoms you see here is that the polonium-218, the bismuth-214, and the polonium-214 all have the opportunity to decay by the emission of an alpha particle. Now it's true that the bismuth, for example, has the opportunity to decay by alpha or beta, but predominantly it decays by alpha. And the same is true of the polonium-218. Its predominant mode of decay, for our purposes, is that it decays by alpha emission. And so these three, the polonium-218, the bismuth-214, and the polonium-214, decaying by alphas, make them the dangerous daughters. And you need to remember these three, the two poloniums and the bismuth. Those are the dangerous daughters because they emit the alphas. The alphas are dangerous because they're short range and deposit their very large amounts of energy over just a few cells. So do not forget the two poloniums, 214 and 218, and bismuth, 214, as being the dangerous daughters of radon. Now the units of radiation, we do have some more terminology with which to become familiar. And the units, some of them are depicted here. We see under amounts of radiation, the becquerel, which is not in too common use in the United States, but the becquerel is 1 disintegration per second. The curie, which is a very large amount of radiation, represents 37 billion disintegrations per second. The picocurie, is really just a fraction of the curie, it's 1/trillionth of a curie, is 0.037 disintegrations per second, which if you convert that into minutes, that's 2.2 disintegrations per minute. Let's just talk physically about what this means. If you're looking at a curie, if I looked at a certain region of space, it doesn't matter what the volume of that space would be, if I saw 37 billion atoms decaying every second on the average, then I would say that there's 1 curie of radiation in there. If I look into again, a volume of space, and again, it doesn't matter what the volume is, if I see 2.2 disintegrations each minute, if I set my watch for 1 minute and I watch this volume of space and I see 2.2 on the average atoms decay every minute, then I'd say there's 1 picocurie of radiation in that in that space. Now, of course, that doesn't tell the whole picture of what the effects of radiation is or what the health risk is, because it doesn't tell us whether it's alphas, betas, or gammas, or how much energy, or what the dose is. But it does give us a beginning of what these radiation units mean. Now, to make the picture more complete, we will look at a few more units, one of which you see here is the rad. And I've written it out. The rad is simply the energy absorbed per kilogram of matter, and it happens to be 0.01 joules per kilogram. Now, what the heck does that mean? Well, the joule is a unit of energy. It's very similar to the kilowatt hour, the gallon of gasoline, etc. It's just another unit of energy. It's similar to the electron volt. And what the rad is, and I've gone out and gotten this 1 kilogram mass here, and so this thing weighs a couple of pounds, and if we have 0.01 joules of energy, however much that is, strike this mass, then we would say that this mass of 1 kilogram has been exposed to 1 rad of radiation. Okay? The further units are the gray, as you see here, which is really just a unit of rads. It's 100 rads. That's all that is. And again, the gray is not in very common use. And yet, that still does not complete the entire picture, because we still have to take into account that if you're struck with 1 MeV of alpha particles, there's a certain health risk. If you're struck with 1 MeV of gamma rays, the health risk is much smaller, because the gamma rays have very little interaction with matter. And so somehow we need to take into account, beyond just the number of rads, that is the amount of energy per pound or per kilogram that you're absorbing, we have to take into account what particles are striking you that are carrying that energy. And for that, we invent this parameter called the quality factor. Now, bear with me, all of this will make sense to you in just a minute. In the quality factor, it's a measure of how dangerous the different radiation types are given the same amount of energy. And you see here that the alpha particle has a quality factor of 20 as compared to the beta particle or the X-rays that have quality factors of 1. What this means is that if you had an MeV of alpha particles strike you, it's 20 times more hazardous than if you had that same energy, the MeV of beta particles strike you. It's 20 times more hazardous. The proton has a quality factor of 10 and the neutron 5. So this gives us a method by which we can come up with another parameter that takes into account the type of radiation and the amount of energy that that radiation is carrying. And that quantity is called the REM, R-E-M. And it's simply equal to the number of rads to which you're exposed times the quality factor. Another set of units similar to this is the sievert, which is the gray times the quality factor. Remember that the gray is 100 rads, and again, you don't see this in very much use. Beyond this, we have exposure rates. That is, how many REMs do you get per hour or per year? And you see there are REMs per year, millirems per year, and sometimes millirems per hour. And so, having done that now, let's just take a look at an example or two. Suppose, as you see on this visual, that you have 4 rads of alphas striking a given body. How many REMs is that? Well, the number of REMs, again, is the rad times the quality factor. And so it's 4 rads, so that's where the 4 comes from, and the quality factor is 20, which gives us 80 REMs. Now, 80 REMs would be a very high dose of radiation, 80 REMs. That's quite significant. And we certainly don't get those in our typical radon activities. Let's go on with this example. If you had 4 rads of betas strike you, the number of REMs would be the 4 rads, that is, REMs is rads times quality factor. So the number of REMs would be 4 rads, and the quality factor for betas is 1, so you'd only have 4 REMs. So you see that the REMs from alphas is much higher than the REMs from betas, indicating, of course, that the alphas are 20 times more hazardous than the beta particles. Okay. Again, what follows on the very next page is a set of questions, and I would like you to deal with those as you have been doing, and then return to the video at this point. Continuing on with our measurement units, that doesn't end the measurement unit story. There are a few other things we need to be familiar with, and that is we've talked about the amount of radioactivity in terms of rads and quality factors and REMs, but now we also want to talk about concentrations. Now that's activity per unit volume, and the primary concentration unit that we will use is the picocurie per liter, and you see here on the visual that a picocurie, you remember that a picocurie was 2.2 disintegrations per minute. So a picocurie per liter simply represents 2.2 disintegrations per minute per liter. So if I can return to my liter bottle here for a second, if I were to look in this bottle and if I could see the radiation, of course I can't, but if I could see the radon atoms in here, if I could see in this 1 liter bottle 2.2 radon atoms decay every minute on the average, then I would say that the radon concentration in here is 1 picocurie per liter. Okay? So it's just the amount it is the number of decays of radon per minute and a liter. So per minute per liter. So a picocurie per liter is 2.2 disintegrations per minute per liter. That's all that is. Not particularly tricky at all. Now the picocurie per liter, of course, is used for more than just the radon radiation or the radioactivity from radon. The picocurie per liter is 2.2 disintegrations per minute per liter of any kind of atom. It doesn't have to be specifically radon. But of course radon is the one that's of interest to us. Now the radon daughters, if you recall the decay chain, radon produces, remember the 3 dangerous daughters, the 2 poloniums and the bismuth. The daughter concentrations are not measured in disintegrations per minute. They're measured in a different way. And if we take a look at this visual here, it's an attempt to explain that to you. The unit that they're measured in is called the working level. And it's more a historical unit than it is a particularly useful unit. However, it is in common use in the radon industry, and we need to be familiar with this particular unit. Now, remember the 3 daughters, the 2 poloniums and the bismuth, they emit alpha particles, and those alpha particles carry energy. And of course, it's that energy that does us some damage. If, from all those alphas, if you could see that the amount of energy in a 1 liter container were 1.3 times 10 to the 5th MeVs, if the total energy you're going to get out of that container due to those alphas is this much, then you would say that that is 1 working level of daughter products. Now obviously the more energy you get from these particles, the more of those particles there must have been. And so the working level is a measure of the amount or the number of radioactive particles, namely the 2 poloniums and the bismuth, the 3 dangerous daughters. Now, furthermore, there must be some relationship between the number of working levels in a container, for example, and the number of radon atoms in there. Obviously, if I took this container and there were no radon atoms in here ever, there'd be no poloniums and bismuth because they're daughter products of the radon atom. And if I had a lot of radon atoms in here, I'd expect a lot of daughter products, and therefore high working levels. So there is a relationship between the number of picocuries per liter of radon and the number of working levels of daughters. They're connected. And the connection that you need to remember is here, that if you have 200 picocuries per liter of radon, that is equivalent to having 1 working level of daughters. And turning that around, 4 picocuries per liter of radon is 0.02 working levels. Now let me just rephrase that. If you have 200 picocuries per liter of radon in your container, that's, we have 200 picocuries of radon in this 1 liter container, then we also have 1 working level of the daughter products. And as we have both, we have the radon, 200 picocuries per liter, and we have one working level of daughter products in here as well. Okay, both of those things are in here. Now the problem is complicated, unfortunately, because what happens, if you remember, is that the daughters of radon are solids. Only radon in that the whole decay chain is a gas. So the daughters are solids. So if we look at this container, for example, as the daughters are created, some of them will tend to stick to the inside of the container. And if you look at a house, some of the daughters that are created by the radon will stick to the furniture, the floors, the walls, etc. And this effect of removing the daughter products because they will adhere to surfaces in their environment is called plate out. And you see that depicted on this next visual. The effect of removing the daughter products by other surfaces is called plate out. Now, if you didn't have any plate out, 100 picocuries per liter of radon would give you one working level. Now, I know this is going to start sounding complicated, but it isn't. Let's look at this. Let's return to our 1 liter container here. And if I have, let's say I inject into here 100 picocuries per liter of radon. If I could somehow make it so no plate out would occur, then I'd have one working level of daughters. But because the plate out occurs and the daughter products end up adhering to the surfaces of the container, they're effectively removed from the issue. They're no longer in the air. And if they're not in the air, I can't inhale them, and therefore they're no health risk because they're outside my body, or a very, very small health risk. In fact, one that we typically ignore. So, let me just backtrack for a second. If I have 100 picocuries per liter of radon in here, and if there were no plate out, I'd have one working level of the daughter products. But because there is plate out, in order to have one working level of the daughter products in the air in this container, I have to have 200 picocuries per liter of radon on the average. And that's where we come up with our rule of thumb conversion factor that 200 picocuries per liter of radon induces one working level of daughter products in the air. That's because half of the daughter products are swept out by the surfaces in that space. Now, typically, the plate out is 50%. That is, half of the daughters are swept out by the surfaces in the room, for example, that we're looking at. And as you see here, therefore, since half of the daughters are swept out, more radon is needed to have one working level of daughters, which brings us down to 200 picocuries per liter is one working level. You must remember that. Okay, on the average, the plate out is 50%. Now, the plate out runs between, depending on how much motion of the air there is in the room, the plate out will run between, say, 20 and 30%, up to as high as 70%. And the more motion you have of the air, the more plate out you can get. For example, suppose we have some radon in this empty space right here in front of me. It's decaying into the daughter products. And if there were no surfaces around, then of course you'd have no plate out. But because there are surfaces around, as those daughter products drift around in the air, they fasten themselves to the dust particles in the aerosols, etc. As they drift around in the air, they can adhere to the surfaces. Now, there's not too much drifting going around if there's no motion of the air. There's some, but not an overwhelming amount. Suppose I were to turn a fan on. If I turn a fan on, now I get the air to move around a lot, and all of those little solids are being blown against surfaces, and they have a greater ability to plate out in that case. So if you cause some commotion of the air in the room, you'll get more plate out, effectively sweeping out more of the daughter products. The radon won't be impacted because it's a gas and it's going to bounce around anyway, but the solids will plate out more. So increasing, and you should note this, put this down on the visual you're looking at now, that the increase in air motion in the room increases the plate out. Now let's take a look at how the daughters are generated in a graphical form. If we were to start with only radon in our container, suppose we inject some radon in the container, no daughter products at all initially, we've put pure radon in it. As time goes by, you see here the amount of radon is going to decay as I've drawn it. The daughters initially, at the very beginning, there are no daughters, and so the curve starts at 0, and the number of daughters will increase as you see here. And the very interesting thing about radon and its daughters is that at some point the total activity, that is how many radon atoms decaying per minute and how many daughter atoms are decaying per minute, come out exactly equal. That total activity comes out equal. And during that region where the activities are equal, the number of decays per minute, where they're equal, that is called secular equilibrium. Now that happens because the radon daughters, which have a half-life, the radon itself, which has a half-life of approximately 4 days, is much larger than the half-life of the daughters. The daughter products have half-lives in the order of minutes and seconds, but the radon has a half-life of days. Remember, it's approximately 4 days. And so because the radon is much longer lived than the daughters, you have this effect called secular equilibrium. And it's during this region of time that we usually study the radon problem. That's where the daughter products are in equilibrium with the radon. That is, there are as many daughter products decaying per minute as there is radon atoms decaying per minute, or as there are radon atoms decaying per minute. And it's that region during which we generally calibrate our instruments, etc. So we function principally in that region. Now, how long does it take for that to happen? If you start off by injecting a certain amount of radon in this container, it takes about 3 to 4 hours before the daughter products come to secular equilibrium with the parent radon. And that's why, for example, if you're using charcoal canisters as your detecting device, that after you've sealed the detector, you must wait at least 3 to 4 hours before you start to analyze it, because you've got to let the radon decay into its daughter products, since it's during those periods of time that we have calibrated all of our instrumentation. Now, there's a quantity, too, which you also need to be familiar with. And I don't mean to say that as if this is one more thing you need to be familiar with. Frankly, everything on every one of these visuals is touched upon in the exam. And so you really need to be familiar with all of this material. But in any case, the equilibrium ratio, another quantity, is defined as the actual daughter concentration divided by what the concentration of the daughter products would be at secular equilibrium. Now, I have an example of this that we're going to do here in a moment. And I think which will help clear this up. If you wait long enough, but not too long, you'll have secular equilibrium. Well, how long enough? How long is long enough? 3 to 4 hours. Certainly if you wait 4 hours, secular equilibrium will have occurred between radon and its daughter products. Now, you need to be able to calculate the equilibrium ratio, and fortunately it is not too difficult to get. So if we take a look at this next visual, we'll do it by example. In a room, let's assume that we're in a room and we have 100 picocuries per liter of radon and 0.6 working levels of daughter products. In other words, what we have here is we've gone into this room with 2 different instruments. One that measures the radon concentration, perhaps a charcoal canister, and one that measures the working level of the daughters, one that measures how much energy is coming off of those 3 dangerous daughters, the 2 poloniums and the bismuth. So we have 2 different measurements, we have 2 different instruments that went in and did this. Now, and what I want to get is the equilibrium ratio. That is, we know how many radon atoms we have now. We have 100 picocuries per liter of them. And we know how many daughters we have. We have 0.6 working level of daughters. And to get the equilibrium ratio, remember, it's the actual daughter concentration, which is the 0.6, divided by what that concentration would be at secular equilibrium, and that is without plate out. That is without plate out. You see, at secular equilibrium, without plate out, 100 picocuries per liter is 1 working level. And so, again, the equilibrium ratio is the actual daughter concentration, 0.6, over what would the daughter concentration be if we were at secular equilibrium with no plate out. Well, with 100 picocuries per liter of radon, the daughter concentration would be 1 working level without plate out. And so the equilibrium ratio is 0.6 over 1, or 0.6. Now that may seem a bit much to try to remember, but physically, I personally prefer doing problems this way, to physically work my way through them so that they make some sense. If you prefer, however, I can give you a formula, which we have right here on this next visual, by which you can simply plug in the numbers and get the appropriate equilibrium ratio. Here you see the equilibrium ratio. I've written it as the working level that you measure with your working level monitor times 100 divided by the radon concentration. Again, you have two measurements, the working level measurement and the picocurie per liter measurement, two separate values in a given room at the same time. And all you have to do is plug your numbers into there, and out will pop the equilibrium ratio. Let's do that in the next example. And we see here in this example that suppose we go into a house where the radon concentration is found to be 20. And the daughter concentration, let's suppose that's found to be 0.08 working levels. Well, plugging into that formula, the equilibrium ratio is equal to the working levels times 100 divided by the radon concentration, 0.4 becomes the equilibrium ratio. So you might simply want to remember the formula that the equilibrium ratio is equal to the working level times 100 divided by the radon concentration in picocuries per liter. Now, the bigger health hazard of those two parameters, the radon concentration or the working levels, the bigger health hazard, of course, is from the working level measurement, because a building with a high working level, regardless of its radon concentration, building with a high working level means there's a lot of energy being carried around by those alpha particles, and that's the dangerous part of it. I don't mean to suggest that the radon atoms, when they emit alpha particles, are not also dangerous. But what happens typically is, if there's radon in this room and I'm inhaling it, the radon gets inhaled into my lungs and then exhaled out of my lungs, and as the moments go by, the radon concentration in my lungs becomes pretty much what the radon concentration is in the room. And so that's a certain health hazard. But it is not as much a health hazard as the health risk from the daughters, because what happens when you inhale the daughters, because they're solids, is they adhere to your lungs. And so we inhale the daughters, and when we exhale, they don't all leave. Some stay behind. So we actually build up the number of daughter products in our lungs. We inhale them, actually plating them out of the room and onto the surface of our lungs, where they do the health damage. And so the daughters, the working level measurement, is the bigger health risk. Okay, so let's take a look at the upshot now of what we've just covered in the last 5 or 10 minutes. And what we see here is the more ear movement, the more plate out, and the more plate out, the lower the equilibrium ratio. Let me talk about that for a second. If we could lower the equilibrium ratio, let me do this differently. Suppose we could lower the number of daughters, radon daughters, in the room. That is, we put some radon and somehow we put a filtering mechanism in that as soon as the radon decays into its daughter products, we extract the daughters somehow, we filter them out. If we could remove all the daughter products, then the working level would be 0. And there'd be practically no health risk. Well, certainly no health risk from the daughter products, which are the greater health risk. And so if the working level were to be 0, that is, we sweep out all the daughters, if the working level is 0, what does that do to the equilibrium ratio? The equilibrium ratio would also be 0. So the lower the working level, that is, the lower the number of daughters, the lower the equilibrium ratio. And that's what I'm saying here. The more ear movement, the more plate out, the lower the equilibrium ratio. The lower the equilibrium ratio, the lower the health risk. And health risk is most dependent on working levels. Well, that's quite a bit of material, and to give you some exercise and to reinforce the information into your mind, I've again placed the series of questions with which I would like you to deal at this time and return to the video at this point. There is one more unit with which we need to be familiar, and it has to do with the effect that the health risk depends not only on the concentration in which we're immersed, but also on how long we spend in that concentration. Obviously, if you spend a long time in a high concentration, the health risk is greater than if you spend a short time in that same concentration. And so somehow the time needs to come into play. And it's brought into the game by the development of a unit called the working level month. And what the working level month is simply an exposure to one working level of radiation for one working month. Now, this is actually a very old unit, invented, I don't know when, but at least 40 or 50 years ago. And one working month is 170 hours. If you figure 40 hours a week for a little more than 4 weeks a year, 4 weeks a month rather, you get 170 hours in a month. And so the working level month is very easy to calculate. You just take the number of working levels to which you were exposed, and you multiply that by the number of months that you were in that working level. Let's look at a very straightforward example. Here you see that we've chosen that a person is exposed to 0.01 working levels for a period of 8 hours. So perhaps this person was working in a basement where the radon daughter concentration was 0.01 working levels, and he was in that basement for 8 hours. Now, how many working level months has he been exposed to? Well, the working level month is simply the working level, 0.01, times the number of months. Now, in this case, the number of months is 8 hours divided by 170 hours. You always take the number of hours divided by 170. And if you work that number out, you see here that this becomes 0.00047 working level months, a very small number. And typically, that will be the kinds of exposures that you will see, 0.0003 working level months or 0.0004 working level months. If you do a calculation and you find that an individual was exposed to one working level month, my first guess is that person probably was not exposed to that. You probably made a mistake in the calculation. In any case, to give you a little exercise on this calculation, I've placed a few more questions on the very next page. And I'd like you to deal with those again and then return to the video at this point.